So hello everyone, welcome back to this week's algebraic graph theory seminar. This week we have Dave Morris to talk about automorphisms of direct products of some circulant graphs.
Okay, I certainly want to thank the organizers for inviting me to speak. I am going to talk about automorphisms. Whoops, I'm not working here. Let me see. Yeah, there we go. Okay, I'm going to be talking about automorphisms of products of graphs. So let's just start with some background on graph products, and then I'll talk about the new material. So a product of graphs is just a way of taking two graphs, maybe call them X and Y, and constructing a new graph called X times Y. And the most important examples of products, so there are lots of them, but the most important are probably the Cartesian product, which is usually denoted by a square, the strong product, which is a square with an X in it. And the one I'm going to talk about today really is the direct product, which is just a times sign. The other two are just going to be used as examples, well, to contrast with what I'm talking about. In all of these three cases, it's not true for all products, but for these products, the vertex set of the product is just the set of all ordered pairs where you take a vertex of X and a vertex of Y. So you can think of it as just being the vertex set of the product is the product or Cartesian product of the vertex sets. So every vertex is an ordered pair. I'm not going to tell you exactly what the Cartesian product or strong product is. If you know what they are, that's great. But even if not, it's enough just to know that the vertex set, for what I'm going to talk about, the vertex set is the Cartesian product. Then there's a way of setting up edges. So let me explain though specifically what the direct product is, because that's what I'm talking about. It's also called the categorical product or the tensor product or the Kronecker product. And I think there are probably other names too, but I'll call it direct product today. And here, remember, the vertices are ordered pairs. So if you have two ordered pairs, I need to tell you when to connect them by an edge in the direct product. And it's sort of the most obvious thing. There's an edge from an ordered pair if in the original graphs, there's both an edge in X and an edge in Y between the corresponding vertices. So for example, if we take this graph here, maybe a frying pan graph, I don't know what you call it, and cross that with just K2, well, the result, since there's two vertices in K2, we'll get two copies. I mean, the vertex set will be two copies of the vertices of the blue graph. And I don't know if you can sort of see theirs here, but overall, we sort of see the frying pan, but every vertex has been doubled because we're crossing with K2. And then the edges in the direct product are these crossing edges. Each edge in the original graph gives you two edges in the new graph, and they cross. That's what the direct product looked like. And our most important example will be just crossing with K2, where you do just get this picture where you take two copies of the original graph, throw away the edges, instead put in those crossing edges. So one thing is that if you look at this definition, it should be clear that X and Y are symmetric. So the graph, this product is commutative. If you take X times Y, it's going to look just like Y times X. And it's also associative. If you have three graphs, X times Y, and then multiply by Z, that's going to look just like X times Y times Z. And in fact, in the direct product, it's just that here the vertices are triples, and there'll be an edge if and only if there's an edge in all three factors. But anyhow, all three of these products have these basic properties. And one of the important facts about the direct product, which will certainly come up later, is that if you take the direct product of any graph with K2, the result will always be bipartite. And the reason is that the vertex set is X cross, well, let me call the vertices of K2 0 and 1. The vertices come in two parts. There's X cross 0, or the vertices of X paired with 0, and the vertices of X paired with 1. And there's no edges within either of these layers. The edges all go between the layers. And in fact, this is a very important bipartite graph. It's called the canonical bipartite double cover of X. So if you have a graph and you want to make a bipartite graph out of it, this is at least one of the natural ways to do it. There are other ways, but this is the standard way to take a graph and make a bipartite graph out of it. Just cross it with K2. Right, so as a simple exercise, so we're still just talking about general theory of graph products. Choose any of these graph products I've talked about. Either you can pick it, you can take either the Cartesian product or the strong product or the direct product, call it star. it actually could be any product as long as it has this property that the vertices are just ordered pairs, show that every graph can be decomposed into prime factors. Any graph can be written as a product of smaller graphs where each of these factors cannot be broken up into smaller pieces. And that's just an obvious, I don't know, Dutch argument, what do you want to say? If X is not prime, then it can be broken up into two pieces. If those pieces aren't prime, you break them up. But since we're talking about finite graphs that can't go on forever, you're going to get a product of pieces that can't be decomposed any further. So that's basically trivial. Every graph can be broken up into prime, has a prime factorization. What's not obvious is that that prime factorization, if X is connected, will actually be unique. But that's not a general fact. That's true for the Cartesian product and for the strong product, except, well, it can't be exactly unique. It's just like the prime factorization of numbers. 6 is equal to 2 times 3, and it's also 3 times 2. The prime factorization is unique up to permutation of the factors and up to isomorphisms. Everything's done up to isomorphisms. So any graph has a prime decomposition if it's connected. Unfortunately, I mean, this is a fact, I just want to mention this since we're talking about general theory, is that the prime decomposition is not going to be unique if you don't assume your graph is connected. Oh, sorry, no, for direct product, unfortunately, this theorem simply does not hold. For example, if you take the canonical double cover of this sort of triangle graph, it can be decomposed in a different way, and neither of those graphs can be cut up smaller. For example, this one has a prime number of vertices, so it certainly can't be made smaller. Certainly can't be decomposed. But in general, even for the Cartesian product and strong product, the prime decomposition is not going to be unique if your graph is not connected. And let me just quickly explain why that's true. I think that's kind of interesting. So this is a little different. Let's just talk about high school algebra. Here's a polynomial. I'm going to multiply it by another little polynomial. It's easy to see that what you're going to get is just all the powers from 1 through 6, but you can write that a different way. You can also take the even powers and then just multiply that by 1 plus x. This will, oops, no, I wrote that wrong. What did I do here? Oh, because that shouldn't have been a 6 there. That should have been a 5. That's my bad. 2 plus 3 is 5, not 6. Yeah, so you get all the powers up to 5. You can also get them this way. So there's two different decompositions. You can say that that's a decomposition in the polynomials with integer coefficients. That's certainly two different factorizations, but these are not prime factorizations because this polynomial here is not irreducible. You can factor it as what, 1 plus x times something. You can factor out a 1 plus x. But if we require our polynomials to have the coefficients of our polynomials to be positive, then it's not hard to see that this is a prime factorization. All 4 factors here are indecomposable, so we've got two different prime factorizations. Well, that's to make that relevant to what I'm talking about today, just let x be a graph, maybe K2, for example, and then think of sum. The addition is just disjoint union, and then multiplication is just repeated multiplication, where multiplication is Cartesian product. So this simple high school formula gives a non-unique factorization of a graph if it's not connected. So today, I'm going to assume my graphs are connected, both because anything I talk about would reduce to the case of connected graphs, but also because a lot of things I say won't even be true. Like you don't even have prime decompositions or uniqueness of prime decomposition if graphs aren't connected. So I'll generally assume today that graphs are connected, but let me get back. But we don't have, unfortunately, a unique prime factorization for the direct product. Okay. So let me get back to what I'm talking about. I want to talk about automorphisms of products. Well, all 3 of these products that I mentioned, I didn't define 2 of them, but if most people here probably know what they are. All 3 of them, and certainly the direct product, is a natural construction. In terms of graphs, it's just defined in terms of which vertices are adjacent. And so that means that if you have a graph x, well, if x is isomorphic to some other graph, maybe x prime, and y is isomorphic to some graph y prime, then the direct product, in fact, any of these products, will be isomorphic to the product of the isomorphic graphs. The product of isomorphic graphs is isomorphic to the product of the graphs. More specifically, if you have a particular automorphism from x to x prime and a particular automorphism from y to y prime, Well, the vertices here are just ordered pairs in little x and little y. You can apply alpha to x and alpha to y to get an automorphism we'll call alpha cross beta. So alpha to x and beta to y gives you an automorphism alpha cross beta. That will be an isomorphism of the graphs. And so that means in particular, if you take, take x prime equals to x and y prime equal to y, if you have an automorphism of x, so x prime equals x, and an automorphism of y, putting them together gives you an ordered pair. Well, the set of all possible ordered pairs is the direct product of these groups. Any ordered pair of automorphisms is an automorphism of the product. So this group is contained, the direct product of the automorphisms groups is certainly giving you some of the automorphisms of the group, but it definitely does not have to be all of them. For example, we know that it's contained, if equality holds, then certainly x cannot be equal to y, because there's an automorphism here that doesn't come from the separate factors. The automorphism, you can just interchange x and y. Just interchange x and y, flip the two factors. That gives you an automorphism that doesn't come from just taking automorphism of x and an automorphism of y separately. It mixes x with y. It gets confused about which vertices are x and which vertices are y. And if you think about it, in fact, x doesn't have to be isomorphic to y. If just some part of x is isomorphic to some part of y, you could switch those two factors. The automorphism group gets confused about those. So if equality holds, so this inclusion is totally trivial. If equality holds, then in fact, x and y have to be relatively prime. So that's going to be a standard assumption here as well. I'll assume that my graphs are relatively prime. Otherwise, we'll get some automorphisms we didn't expect that aren't so obvious. Well, the theorem is that the converse is true. If x is relatively prime to y, then we have equality. Every automorphism is one of the obvious ones that just comes from the factor, but that's only for the Cartesian product. This was proved long, long ago. Chris and I were alive then. Yes, we have to assume x and y are connected. Otherwise, like as I said before, things are completely different in the disconnected case. Actually, the same is also true. I'm talking about there's lots of products people could consider and people do consider. I've talked about Cartesian product. There's also the strong product. The converse is also true for the strong product, except that there you need another technical condition. I'm not going to tell you what the condition is now, but we'll see it later because it's going to come up later in the talk. But yeah, so essentially we understand the automorphism group of the product of the graphs of the product of the Cartesian product or strong product of two relatively prime graphs. So the bad news, though, is that the converse is not true, definitely not true for the direct product. So in short, the point of what I've been talking to up to this point is that we simply do not understand the automorphism group of a direct product. So I'm assuming x is connected, assume x is relatively prime to y, make all the basic assumptions. We just simply do not understand the automorphism group, even in the stupid case where y is K2. Just take x, cross it with a two vertex graph. We do not know what the automorphism group is. So in fact, this special case K2 is so important it has a name. We say that x is unstable if the automorphism group when you cross with K2 is not just the obvious ones. And it's unstable if there's an unexpected automorphism of this product, if it's not just the product of the automorphism group. So let me just say, so what's happening here with K2, the x cross K2 has two layers. One thing you can do is just move the two layers simultaneously. That's an automorphism of x. The other thing you do is switch the two layers. That's an automorphism, that comes from an automorphism of K2. Those are the obvious things, just moving around the two copies simultaneously in lockstep or switch the two layers. Those automorphisms are obviously there. The bad case or unstable case is when there's some other automorphism that does different things to the top than it does to the bottom, and it just came from nowhere, basically. We don't understand those automorphisms. But that's what I want to talk about today. I want to understand which graphs are unstable. When are there automorphisms that we didn't know about that weren't obvious? Well, to talk about that, I need to make one more definition. I think everybody knows if you have a permutation of the vertices of x, that's an automorphism if it preserves incidence. there's an edge from V to W if and only if there's an edge from alpha V to alpha W. That's a very standard definition. What we need to understand unstable graphs is a souped up version. We say that we have we all know what an automorphism is. A twofold automorphism is not just a single permutation, but a pair of permutations. Let me call them alpha 0 and alpha 1. And you can think of it as being a permutation of the bottom layer and a permutation of the top layer. So we've got a permutation in an, well, okay. And then all we do is now we've got two alphas. And there's two alphas in the definition, just change one of them to alpha 0 and the other one to alpha 1. So a twofold automorphism is a pair of automorphisms that together respect incidence. So V gets moved by one permutation, alpha gets moved by some other, W gets moved by some other permutation, and those two together work. Edges go to edges, but we've moved V and W by two different permutations. So the obvious twofold automorphisms are just when you take alpha naught and alpha 1 to be the same thing, just to be an automorphism, because the twofold thing was just that we changed the two alphas to different things. So one way to get a twofold automorphism is just to take a pair of automorphisms. Those are the obvious ones. It turns out that the non-obvious ones exactly give you an unstable graph. So assume just that we need a connectivity assumption. Let's assume that X cross K2 is connected. And another way of saying that, that's the same as just saying, well, first of all, X better be connected, but also X shouldn't be, well, X cross K2 is bipartite. If X was already bipartite, making up the bipartite cover of a bipartite graph gives you something disconnected. So let's assume that X is connected and not bipartite. It's an exercise to show that X is unstable if and only if it has a twofold automorphism that is not obvious, not just an automorphism doubled. And the idea is, let me just give you the hint. So from going from right to left, if you have a twofold, you've got two permutations of the vertices, put one of them on the bottom layer, do alpha 0 on the bottom layer and alpha 1 on the top layer. It's the exercise. So if you define alpha of an ordered pair to be just the corresponding permutation, depending on which layer on, this definition here exactly says that edges will go to edges. And then conversely, you need to show that if it's unstable, then in fact there is, yeah, you just take the permutation on each layer. All right, so that means to tell, so when I'm asking for unstable graphs, I'm asking for graphs whose double cover has an unexpected automorphism. That's the same as trying to find a twofold automorphism of the original graph. With that in mind, it's easy to see, there's an easy condition that implies that the graph has one of these automorphisms that's unstable. It's going to be unstable if X has what we call twin vertices. I'll explain what that means in just a second. And that's even if X is connected, even if it's not bipartite, whatever. Okay, so let me explain. So this is an exercise. Do this either take it on faith or do this for yourself. So I'm assuming X has twin vertices. Twin vertices are vertices that have two different vertices that have exactly the same neighbors. So let's say that A and B are twins. That means that the set of all neighbors of vertex A is exactly the same as the set of all neighbors of vertex B. That's the definition of twin vertices. Well, that's the same as saying there's an automorphism of the graph that interchanges the vertices A and B. So I've got these two vertices that each have the same neighbors. We just switch those two, but leave all of the other vertices where they are. And the point is, since they're twins, none of the other vertices will realize they've been switched, because if there was an edge to A, there's also an edge to B. That will be an automorphism. And then in order to get a twofold automorphism, I need to get another automorphism, but I can just let alpha 1 of V just be the identity map. And the point is, if you think about it just for 1 minute, you'll see that that will be the two of them together make a twofold automorphism, because we have twin vertices. So there's several reasons why obvious reasons why a graph might be unstable. If X is not connected, then automorphism groups are definitely confusing. If X is bipartite, then again, we have a connectivity problem. And maybe the first one that's a little bit interesting, but it's still considered trivial, is if X has twin vertices. Okay, so The bad news, as I said, is that we don't understand the automorphism group of a direct product, even in the stupid case where y is K2. The good news is that the only case that we do not understand is when X is bipartite. That's because of an old, not quite as old theorem of Dörfler that says exactly that the automorphism group of a direct product is the direct product of the automorphism groups if, well, first of all, we have to make the basic assumptions. We need our graphs to be connected. There shouldn't be twins, otherwise we know that we've got a problem. And then if we assume they're not bipartite, that's the theorem, okay? And also, I guess we have to assume, of course, they better be co-prime, otherwise, yeah. So if you make the assumptions that we know are necessary, then the converse is true. We understand the graph completely. And so let's look at the bipartite case. Suppose X and Y are bipartite and assume they have more than one vertex, otherwise there's a triviality problem. Well, then X cross Y will not be connected. The point is just that X breaks up into two parts and Y breaks up into two parts. And because they're bipartite, when you take the direct product, all the edges will go in this cross sort of pattern. So we'll get, yeah, one part of X and the other part of Y will be one piece, and then yeah, one part of X, the other part. Yeah, the graph will not be connected. And then it's easy to get an unexpected automorphism. If you take an automorphism of X and an automorphism, if X and Y both have non-trivial automorphism group, the point is you can just do something, put some automorphism, some non-trivial automorphism on this connected component and the identity map on the other connected component. That's not going to be one of the automorphisms you get just by taking X and Y, treating X and Y separately. We've mixed X with Y. All right, so bipartite's a problem. So this is what I'm trying to understand. I'm trying to understand this problem that we don't understand the Cartesian product. But the problem only arises when the graphs are bipartite. Well, if neither of them is bipartite, well, then we do understand. There is no bad news. That's Dörfler's theorem. On the other hand, what I just said, the exercise with if both of them are bipartite, then it's bad. The automorphism group does have things unexpected that we don't understand. So the open case, if they're both bipartite, we understand that it's bad. If it's not bipartite, well, I mean, the question is which graphs are bad? If neither graph is bipartite, Dörfler says we understand the automorphism group. If both graphs are bipartite, it's bad. So the open case where we don't know whether the automorphism group is only what we expect, we don't know whether X is stable or not, is when X is not bipartite. Well, one of the graphs is not bipartite, say X is not bipartite, and the other graph is bipartite. So let's say Y is bipartite. Well, the simplest case of a bipartite graph would be K2. That's the case to look at just to get started. So one reason why I said it this, well, yeah, the reason today I'm going to talk about just X cross K2 is because it's the starting point. We'd really like to understand all bipartite graphs, but it's important to start with the easiest one. So I just want to start, until we understand X cross K2, we're not going to be able to understand X cross every bipartite graph. And another reason is just that, remember, X cross K2 is the canonical double cover. That's a graph that people study it's of its own interest. So it's important to understand its automorphism group. But I think maybe a better reason, I think those are both good reasons to start with, but a better reason is that K2 is not just the simplest, easy, special case. It's actually the main case. It's the main case that we need to understand if we want to understand which graphs are the automorphism group of X cross Y in general. So here's a fact. I think it must be in the literature. So if somebody can give me a reference, that's great. I wasn't able to find it. Let's assume that X is stable. So let's assume we understand the automorphism group of just X cross K2. We're trying to understand the automorphism group of X cross any bipartite graph. Well, let's just start with X cross K2. Well, and also assume X is not bipartite, otherwise we have that connectivity problem. Then in fact, if you cross X with any bipartite graph, if you cross X with any bipartite graph, the automorphism group is just what we expect. So it's not just that K2 is a case to consider, once you understand K2, you actually understand all bipartite graphs. So K2 is definitely the graph to look at. It's the simplest graph that gives all the answers. But here, of course, I didn't say it, but I have to assume that X is co-prime to Y. Otherwise, this definitely isn't true. And the thing is that we have to assume X co-prime to Y. It's not the obvious definition. There's a definition of co-prime that makes this right. But for example, if X and Y are just circulant graphs, then saying they're co-prime would mean, for example, it'd be enough to just assume that the number of vertices are relatively prime. So yeah. So co-prime isn't, let me not go into exactly what co-prime means here, but it's, there's a product and you have to show that there's no factors in common. All right. Okay, so I want to understand, we're trying to understand the automorphism group of X cross K2 because that would help us understand the automorphism group of X cross any bipartite graph. And Steve Wilson, quite a while ago, just asked about the special case of circulant graphs. So a basic question, let's just look at, we don't understand in general, let's just talk about circulant graphs. Which circulant graphs are unstable? Which circulant graphs are bad? Which circulant graphs have a canonical double, which circulant graphs are there whose canonical double cover has an automorphism we didn't expect? Well, actually, this isn't exactly the way he phrased it because there's some obvious circulant graphs that are unstable. If the graph isn't connected, then there's definitely a problem. We've talked about that. If the graph is bipartite, there's a problem. So let's not worry about bipartite graphs. So I guess we should say we know, we know the answer. And then if the graph's bipartite, there's going to be automorphism you didn't expect. If the graph is unstable, or if the graph has twins, it's unstable. So the question is, after you rule out the obvious reasons for a graph to be unstable, which other ones are there? And the answer is very easy. There's none. There are no connected, there's some obvious reasons why a circulant graph might be unstable. Those are the only reasons. Unfortunately, this answer only works if the number of vertices is odd. So I said we don't understand the automorphism group of X cross K2. Well, we do understand it if X is circulant, which is all I'm going to talk about for the rest of the day, circulant graphs. If the number of vertices is odd, then there are no unexpected automorphisms. Your graph is stable. And working with two mathematicians from Slovenia, Ademir Hujdurović, the student Đorđe Mitrović from both at the University of Primorska, we extended this. So there's no bad graphs with an odd number of vertices. What we figured out is exactly which vertices are ruled out, which numbers of vertices are ruled out. So there's no unstable circulant graphs. There's no unexpected unstable circulant graphs of any order n if either n is odd, so that we already knew, but I'm going to give a list of exactly which orders have no unstable graphs, or small graphs aren't big enough, small graphs, or the last case is if it's 2 times a prime number. If n is 2 times a prime number, then there won't be any bad graphs. Well, actually, the prime better be congruent to 3 mod 4. So there's no examples when n is odd, and the hope was there wouldn't be many examples when n is even, but actually this is a very sparse set. If you take almost any even number, in fact, take any even number that's bigger than 8, it doesn't have to be 2 times a weird prime. So that's almost every even number. There will be some graphs that we don't understand. There are some graphs that have unexpected automorphisms. So this was very good news about the odd case, and I assumed it would carry over to a lot of even ones too, but it just doesn't. Most of the time, if pick any even number, almost always you'll be able to find a graph whose canonical double, a graph that's unstable, a circulant graph that's unstable. Okay, so this is the question I want to talk about. I finally got into the topic of today's talk. I want to talk about which circulant graphs are unstable. So let's assume that X is a circulant graph that's not obviously unstable. And also, we could assume that it has an even number of vertices because otherwise it's definitely not unstable by the Fernandez-Hujdurović theorem. What we're trying to do, what I want to talk about today, is characterizing exactly the graphs where the automorphism group of the direct product with K2 is not just the direct product of the automorphism group of the direct product. The automorphism product is not just the product of the automorphism groups. And I want to just say this seems to be uncommon. There's no theorem about this as far as I know. It seems like we ought to be able to prove a theorem, but I did some computer work. I had a computer go all the way up to order 50. It found about just a little bit over 70,000 of these unstable graphs. But, and this is where I'm really not sure. I just did a back of the envelope calculation. I think there's about 3.6 million circulant graphs of even order up to 50. And so if you do the division, do the math there, that's less than 2%. I think that less than 2% of the graphs, of the circulant graphs of even order up to size 50 are actually unstable. 2% is small, but not tiny, but I think that percentage is going to go to 0. That's my guess. And in fact, yeah, from what we understand, it would go to 0, but I haven't proved that. I'd hope that somebody could. It's not something I've thought about carefully. So, okay, we're trying to understand this question. So we're trying to find these unusual graphs whose automorphism group is not what we would expect. Well, we have a partial answer in the same paper where he asked this question. Steve gave some sufficient conditions for a circulant graph to be unstable. In fact, he gave 4 different conditions, called them C1 through C4, that imply a circulant graph is unstable. And let me just talk about a couple of those. So one of them, C4, is I think the easiest to state. So let me do that. A circulant graph with n vertices and connection set S is unstable if, and this is not an if and only if, that's the problem. We have sufficient conditions to be unstable. We don't have good necessary conditions to be unstable. And as if there's some unit in the group of integers mod n, such that when you take m times the connection set, it's just the original. So you take m times the generators, m times the things in the connection set, that will be just S except it's translated by n over 2. That's a sufficient condition. In fact, the proof is saying that the circulant graph is unstable means that we should be able to find a twofold automorphism. We should be able to find a permutation alpha naught and a permutation alpha 1. And this m here, that gives us alpha naught. Alpha naught is just going to be multiplication by m. And then alpha 1, well, if you look here, m times s, yeah, alpha 1 is just going to be translation by, it's m times s. You just translate by n over 2. This condition here will exactly say that alpha 1, alpha naught and alpha 1 will be a twofold automorphism. Neither one is an automorphism by itself, but put the two together and it will be an automorphism. And now if you're familiar with the CI property, you recognize what's going on here. Taking alpha m times x is the usual automorphism of a circulant graph. And it turns out that that's actually all that's being used here. You don't need to know that alpha naught is actually m times x. The same proof works if this here is an automorphism from the original graph to the graph you get by adding n plus 2. So if the original, yeah, if the Cayley graph on S is isomorphic, sorry, the circulant graph on S is isomorphic to a translated circulant graph, then the circulant is unstable. So that's Wilson, that's maybe that's a good way of saying it. I think for people who know the CI problem, this is pretty natural. You got 2 different connection sets that give isomorphic graphs, then the graph is unstable. You got automorphism you didn't expect. Okay, that's one of his conditions. I'm not going to tell you all 4 of them, but let me talk about one other one. Let's talk about C1. But C1, I need a little bit of notation for that. So let's let SE be the part of S that consists of even numbers. And let's let SO, well, so there's the even part and the odd part. That's the thing. And then what Wilson proved, another example, Wilson proved that the circulant is unstable if SE, the even part, is invariant under some translations. So what that means, there's a non-trivial subgroup, let's call it H, so that if you translate the even part by that elements of that subgroup, it's invariant under translation by something. That's it. So that's easy to state. And then again, the proof, once you have the conditions, usually they're not hard, although actually a later one is a little more complicated. But yeah, so just let's take some element of H that's not 0. And we need to define an alpha naught and alpha 1. Well, I can define them both at once this time. We're going to let alpha I of V, well, it's V. So on the bottom layer, yeah, it's V. It's the identity map on the part of the graph. Well, on V0, on the bottom part, it's the identity graph on the evens. On the top part, it's the identity permutation on the odds. And then otherwise, on the other part, it just translates by this element H. So yeah, there's 2 layers. Sorry, no, yeah, okay. Let me not babble. It's, again, these proofs, it's easy to write it. You have to think for a minute to check, but the point is this translation, invariance under translation means that adding H is not going to change. Yeah, it's still going to be, it's going to be an isomorphism. So we can generalize this. Yeah, so this is Wilson's C1. His C2 and his C3 were a little more complicated, but it turns out C1, C2, and C3 can all be combined into something that generalizes all of them. And let me just state that this is not, it's not important to understand this, but let me just say it. It's a little more complicated, but you can see it's similar to what we had here. We've got an S plus H. You got to have a subgroup. Instead of just one subgroup, you need 2 subgroups. C1, if you want to look at this a little more, the point is that C1 is just the special case where the subgroup K is the entire group Zn. And let me not explain why C1 is a special case, except to say that you can sort of see it here in either case here. S, if K is Zn, then the odd part, this is all the odd numbers. S take away the odds, that's S even. So this is just the even part of S. We're adding H that's supposed to be in, well, it turns out it's the same as saying it's in S even. So it's definitely more complicated. And actually this, because it's more complicated, it's a little more complicated to prove, but it's definitely not difficult. It's just working through the details to check to see that you've got an alpha naught and alpha 1 that make a 2-fold automorphism. The details don't matter, but we've got, the point is Steve Wilson came up with four different conditions. One of them we generalized slightly. C1 through C3 we combined as something much more complicated. Well, Wilson conjectured in that same paper that his C1 through C4 were actually a complete answer. They're definitely sufficient conditions for being unstable. He thought that taken together, they were necessary, that any unstable circulant graph would satisfy one of those 4 conditions. That's unfortunately not true. There's a counterexample on 24 vertices that was found a few years ago. And then actually the generalization I've told you about. So C4 could be slightly generalized by using more general automorphisms. C1 through C3 could be generalized in that complicated way. So that provides not just a counterexample, but infinite families of counterexamples. So Wilson unfortunately was not right. We do not understand the automorphisms of which circulant graphs are unstable. On the other hand, so it's not all bad news here. On the other hand, by doing about 40 pages of case-by-case analysis, I and my co-authors were able to show that Wilson was right. Wilson did find all of the unstable circulant graphs if you look at small valency, up to valency 7. So all of the counterexamples have at least 8 valency 8, and in fact, there is a counterexample of valency 8. For example, on 48 vertices, you can make a counterexample, and there are infinitely many. This is the first of an infinite family of unstable circulants of valency 8 that do not satisfy any of Wilson's conditions. But we did more than this. So yeah, so Wilson was right up to valency 7. But the way we did this, we didn't just prove that the graphs of valency 7 or less satisfy Wilson's conditions. We actually found all of the circulants of valency less than or equal to 7 by using its conditions. What we did was we made a list of all unstable circulant graphs of valency 7, but it's not a list. There's a different list for each valency. And the list, I mean, the theorem I stated just a little while ago, or proposition, was fairly complicated. These lists are not complicated. Let me just give you an example. So we have a different list for each valency. We've got a list of the graphs of valency 4, valency 5, valency 6, valency 7. So here's valency 5, for example. So there's a family, take any multiple of 12. There's an unstable circulant graph of valency 12. And in fact, there's a family of them. Just pick an odd number S For any odd number S, you're going to get a circuit unstable circulant to valency of order 12K, any multiple of 12. And that graph, though, anyone, no matter what S you pick, that'll be a graph of Wilson type C1. The evens are invariant under some translation. And then also it happens to be an example, an unstable graph with just 8 vertices. And that one has Wilson type C3. So that's the way it goes. For each valency, we made a list of the graphs, then it's easy to see that each one of them does have a Wilson type. It came from one of Wilson's theorems. So small valency we do understand, but in general, as I've said over and over, it's an open problem to figure out which circulant graphs are unstable. So we have a partial answer from Wilson. He gave 4 conditions that are sufficient. And in fact, we generalized those. So we've got some more general conditions. And there's one other infinite family that we found. So it turns out that so here's the condition, another sufficient condition for a circulant graph to be unstable. If the connected components of the even part, so just take the even generators, if the connected components of that subgraph are unstable and the odd part of the connection set is invariant under a bunch of translations, then the graph will be unstable. And here's the specific statement. I'm just saying this more formally. A circulant's unstable if this here is showing from the even part. If it's unstable, that means there's a twofold automorphism. Well, if you just let H be a certain subgroup, it's the subgroup generated by how far these permutations translate things. And the odd part is invariant under this subgroup, then the graph is unstable. And the proof, again, is quite simple. You just define to be the identity on one part and use these automorphisms we found on the other part. So let me summarize what I've talked about today. So the point is, there's this definition. Some graphs are good, some are bad. The bad ones we call unstable. They're automorphisms. Yeah, we don't understand the automorphism group of X cross K2. And so Steve Wilson asked a specific case, let's look at just which circulant graphs are unstable. Well, some are obviously unstable. If they're not connected, there's a problem. If they're not twin-free, there's a problem. If they're not bipartite, there's a problem. And in fact, there's a special name for this. A graph is called non-trivially unstable if it's not connected or not twin-free or it's bipartite. So what Steve really asked was which circulant graphs are non-trivially unstable. And well, we generalize Steve's examples C1 through C4. And actually we found one additional family, but basically it's Steve's answer. So Steve Wilson found a bunch of examples. We expanded that somewhat to get more examples. And then according to a computer search, so I looked up the graphs of size 50. These examples we found do include all of the graphs up to size 50. So it's a complete list up to size 50 as far as we can tell. But beyond that, I don't know. So we're trying to understand which circulant, you could look at all graphs. We're just looking at circulant graphs. We're trying to understand which ones are unstable. It certainly could be the case that there are infinitely many more examples for larger orders. So I guess the summary is, I've talked for 45 minutes, but it's the same thing I said right at the start. We simply do not understand the automorphism group of X cross Y, even if X is the simplest kind of graph, just a circulant graph, and Y is even the simplest kind of simple graph, just K2. We do not understand this question at all. We tried to give some information about it, and I hope maybe somebody else can take it farther. Thanks.
Thank you. It's a very nice talk.
Okay, thank you.
So is there any question for Dave?
So Dave, you say that the circulant graphs are sort of the simplest case. Have you looked at any other, like, are you, is that necessarily the simplest case?
You're right. From my point of view, so I study Cayley graphs. So among
Right.
Cayley graphs, the simplest graphs are obviously the circulants. But as I was saying that, I realized, oh, maybe somebody should look at trees or something like that. Yeah. So I'm sorry, I have a very biased point of view here. What, Chris, you gonna tell me something easier than circulants in the family of Cayley graphs? Yeah. So
Well,
no, I think,
cube-like
yeah,
graphs.
I don't know what's.
Yeah, are they
I'm
cube-like
not a
graphs?
graph theorist.
Okay.
Sorry, what?
Are the cube-like graphs more complicated?
Sorry, the what like?
The cube-like graphs?
Cayley graphs with Z2 to the D.
Oh, cube. Okay, I thought you said cube like a cucumber. And I was trying to think, what the heck does that mean? I see. So I see. That's a good. Oh, shoot. Oh, those are bipartite. So, oh, you take
No.
Cayley graphs, a non-bipartite Cayley graph on Z2 to the N. Ouch. Yeah. So, okay. That's definitely a good question, but my certainly with the kind of ideas that we were using, I mean, we did this long case by case analysis, having all those elements of order 2 would be a nightmare. I mean, if there's no element of order 2, if you have a circulant graph of odd order, there are no unstable graphs, and that's because there's no element of order 2 to worry about. And now, as soon as you get to 2 times an odd number, even square-free, circulants of square-free order, we don't understand. And if that element of order 2 weren't there, there wouldn't be a problem. And now what you've done is you're saying, let's instead have everybody be of order 2. I mean, it looks to me like it would be bad, but yeah, again, I've got a very skewed perspective on this problem. But yeah, life is, yeah, the more even it gets, the worse it gets, at least from our perspective. But it may just be that we're looking at it the wrong way. But yeah, that's a very good question. Yeah, even among Cayley graphs, I said obviously the circulants, but you're right. Elementary abelian 2 groups. Well, yeah, elementary abelian P groups for odd P's. Yeah, those are the best. Those are even better than circulants. Yeah, but P equals 2. Boy, yeah,
Well,
okay.
when P is equal to 2, if you're looking at the product of your cube-like graph with K2, you're actually just looking at a Cayley graph, another cube-like graph.
That's right. Yeah.
So, and so to some extent, you're asking which connection sets is the Automorphism group, which connection sets are GRRs.
That's right. Yeah, that's the idea here. Yeah, it's almost going to be a GR. At least that one generator has to be. That's what it is. That one generator has to be fixed by all automorphisms. Yeah, you color the edges for that one generator. Yeah. Well, actually, no. There's more. Yeah, that's it. That is it. Yeah, I guess that's the thing. What? Yeah, that's another way to say the graph is stable. Is if you color those edges and that set of edges is invariant under the automorphism group. Yeah. If that color class is invariant, that's what stable means. So yeah, that. Yeah, and yeah, so you actually know GRR, Chris. Yeah, that sounds like it's going to be, that can't always be true. Yeah, it's obviously not always true.
I mean, that's
maybe you can come up, yeah, if you can come up with some simple condition.
Characterization looks a little,
yeah, characterization is what you want. But yeah, you've just got, and all elements of order 2 look the same. So how are you going to pick out that one to be the one that's preserved?
I mean, I think you might be able to prove that, well, I'm not saying it's true, but you might be able to prove that for most things they are stable. We're probably going to 1.
Yeah, that's right. That makes, yeah, if you have a non-bipartite cube-like graph, now they learned this term, yeah, probability 1 makes sense. Just from, well, that's why also I figure that, yeah, I think people expect unstable circulants to be unusual, but nobody's proved anything, but it should be provable. Yeah. But yeah, you're right. Cube-like, yeah, it's going to be a different.
Yeah,
type,
I think it might be true that if you pick a random cube-like graph, that you're stable.
Yeah, makes sense. I guess actually I should say, so if, yeah, so yeah, so I was, yeah, Steve Wilson, yeah, I've learned lessons. So Steve Wilson thought he'd found all the conditions. We showed he hadn't found all the conditions. We thought we'd found all the conditions, but then we found that last infinite, just a computer. I mean, so I ran the computer up to 50 and around, like, I forget, the smallest one was 44 or 46 or something. I thought, you know, we'd gone past 40, we had them all. And then suddenly this example popped up and I was like, where did that come from? And I realized it's this thing about if if the even's unstable and the odd's invariant. So I think it's likely that there's still more families to come, but if these were clearly, our families are measure zero, almost no graphs are in one of our families. And that should be the case.
Yeah, that seems very plausible.